Understanding Eddy Current Testing, ET, Module 18, Weld Inspection Mastery, Complete NDE course. Gary Pace, PE Welding Engineer, Katy, Texas. So what is eddy current testing anyways? Well, eddy current testing to me is black magic. No, joking. It uses electromagnetic induction, and we run some electricity through a coil, and the electrical currents are induced into the test specimen, and then any changes when these electrical currents are induced into the test specimen, any discontinuities are going to change that current flow and whatever, and it's going to be monitored and analyzed. The advantage of this over other methods is we don't need direct contact and we don't need a couplant, meaning we can use a probe, and it's not like with ultrasonic testing where we're going to have to use a couplant and then we got to wipe that stuff off and clean up afterwards. So a lot of times we're going to use this in aerospace, tubing, and other manufacturing industries.
Eddy current testing uses the principle of electromagnetism as the basis for conducting examinations. Surface and slightly subsurface detection capabilities. Discontinuities, cracks, and pores can be found. The geometry, scratches and undercut, and then material properties, heat treatment, residual stresses, hardness, phase composition, creep, fatigue, and corrosion. Eddy current testing is one of the standard non-destructive testing methods. It uses electromagnetic fields and is very sensitive to many material and geometric variables. Because it is an electromagnetic test, its signals move with the speed of light and its measurements can be made very quickly. Being electrical in nature, eddy current testing can easily be automated and its signals can be used to control other electrical devices. Because the sensing devices are coupled to the test specimens through electromagnetic fields, the devices do not have to contact that test specimen. Eddy current testing can even be used in a vacuum. For these and other reasons, eddy current testing is extensively used throughout the industrial world. Eddy current testing is the process of electromagnetically inducing small electrical currents into an electrically conductive specimen and observing the changes in the effects caused by these currents on the electromagnetic fields. Every variable that affects the induction of eddy currents, their flow in the material, and the reactions to their electromagnetic field is capable of being utilized as a test variable. Eddy current testing basic principles. The flow of eddy current within the material is disrupted by the presence of discontinuities such as cracks, porosity, or inclusions. Discontinuities cause a decrease in the flow of current in the material by increasing the length of the path along which the current must flow, as shown in Figure 2. This results in a reduction of current flow, which causes a change in the impedance of the test probe coil.
So here's some factors that are going to affect the eddy current signals. Like any other non-destructive testing process, there's going to be some variables that are going to cause things to change or cause the signal to change. So material variables, electrical conductivity of the material, that's going to give us different readings. It's going to affect the signal. Magnetic permeability of the material. What's the heat treat condition? Is this heat treated or is it just in the as welded or as is condition? Hardness and residual stresses. So if you have hardness or residual stresses left over from welding, these are going to show up in the eddy current signals. And then you got geometric variables here like thickness, edge effects, probe liftoff, surface roughness. How rough is the surface? Is it a machine surface or is it something that's just a jagged, craggy mess? That's going to affect our signal. And then discontinuity variables. When we're running this, our eddy current probe across the material, well, discontinuity variables are also going to affect this. And that would be things like crack depth, orientation, and the size and shape of our discontinuity. All of these are factors that are going to affect that eddy current signal.
The eddy current testing signal is strongly related to the geometrical shape of the coil, i.e. the size, shape, and positioning of the coil. The relationship between the coil winding and the suspected discontinuities, the effect of change in lift-off or fill factors, the depth of penetration, and the edge effect. Identifying the various factors causing impedance changes depends on the knowledge and skill of the eddy current testing technician. Thus, selecting the appropriate eddy current testing probe is an important part of eddy current testing. There are three major factors that affect eddy current testing. These are material conductivity, geometry, and permeability of the material being tested. In addition, there are contributors that affect the three major factors. So we see here that conductivity can be affected by alloy, hardness, temperature, residual stress, and coatings. Geometry, thickness, discontinuities, coil to material separation, and then permeability. Is it ferromagnetic? These are things that need to be taken into consideration by the eddy current testing technician. This figure shows a surface probe as it is placed near the surface of a test article. The alternating magnetic field of the coil is essentially perpendicular to the face of the coil. The induced eddy current flows at a right angle to the magnetic fields. Therefore, the induced eddy current flow is parallel to the surface when the surface probe is held perpendicular to the surface. You can see that it sets up a secondary magnetic field created by the eddy current. And then if you have a defect, it's going to disrupt that eddy current. Same setup where we're inducing an eddy current into a material, but you can see where there's a discontinuity, so the secondary magnetic field created by the eddy current is disrupted. So that's what we're going to be able to detect.
So here you can see our high quality graphics that I poached from an Air Force manual. Eddy current basic principles here. So this would be what it would look like if our eddy currents are produced by a surface coil. So we're going to run electricity through that coil, and then our electromagnetic field is going to go perpendicular to that, right? That right-hand rule thing. And then we're going to get a secondary magnetic field that's going to be created by the eddy current, and that's going to be on the surface of our material. And those eddy current paths, they're going to strength decrease with the depth of penetration of what we've got going on. And the material there is a conductor. So we're conducting this eddy current test or examination on some kind of conductive material.
Figure 234 shows an encircling coil installed around a rod. Here, eddy currents flow in the same direction as the current flow in the coil, i.e. around the circumference of the rod. Thus, the encircling coil is especially adapted to locating those discontinuities that are parallel to the length of the rod. The eddy current induced by the internal coil will be the same as the encircling coil, except the eddy current will be concentrated on the inner surface and not the outer surface.
So with eddy current, we've got different probe types, and there's a whole laundry list of things you can do here. We're just doing the rough welding engineering version of this. So surface coils, we're going to use these for surface inspection, and this is like crack detection on the surface or something, maybe the skin of an airplane or something. And then we've got encircling coils, and these are used for tubing and bar inspection. So if you have some kind of bar that you want to check the surface to make sure there's no cracks on it, this would be a good way to do it. And this allows you to inspect the entire circumference of that material. And then we've got inside coils. This would be something that would be sent inside a heat exchanger. So we can check and see if the heat exchanger tubes are have some kind of defect or discontinuity that we need to address. So inspector considerations, the probe size is going to affect the sensitivity of what we've got going on. Coil positioning is going to affect the signal response, right? Where are we putting that coil? Is it close to it, not close to it, wherever? And then proper probe selection is also going to be critical. So these are some things that we need to take into account.
Eddy current testing advantages and disadvantages. Advantages: surface or near surface flaws can be detected. Very sensitive to many variables such as geometry, surface roughness, frequency, electrical conductivity, magnetic properties, and cracks. Direct go, no-go type answers can be obtained quickly. It's portable, no physical contact required, can be accomplished in a vacuum, not too expensive, easily adaptable to production line situations. Electrical signals for electrical controls. Disadvantages: must involve one or more layers and or surfaces that are electrically conductive or magnetic in nature. Requires highly skilled operators when many variables are involved, and adequate separation of variables cannot always be achieved.
Some common applications of eddy current testing: aircraft skin crack inspection. Because aircraft uses a lot of rivets, right? You're punching holes in things, then you're riveting it, then you're flying around the planet, and there's a lot of cyclical stress on there. So they chase down fatigue cracks is what they look for a lot of the time. So they're looking for something that might have a fatigue crack in it. And then they can address it however they do that. Heat exchanger tubing. Heat exchanger tubing, there's a bazillion of those little tubes, and you run a eddy current testing probe down there, and you can figure out, hey man, do we need to address this or what? Surface crack detection. You can find surface cracks in things. You can also measure coatings. What's the coating thickness of something? You can sort materials and verify, because different materials are going to have different responses to eddy current testing. If it's heat treated, or aluminum's going to show up differently than steel. Corrosion detection. We can figure out, hey, do we got corrosion issues here? Are we losing material? And then you can automate it for just a laundry list of other inspection systems. Questions, comments, thoughts, concerns. Gary Pace, PE, welding engineer, Katy, Texas.